We are 4A Games and NVIDIA, and today we will be discussing our implementation of ray tracing in Metro Exodus. So I'd like to start with a quote. My old dream was to see global illumination in an interactive application which doesn't depend on any pre-computation and works with 100% dynamic lighting conditions and a similarly dynamic environment. This is a quote from our CTO, Oles, from some 15 years ago. And as he says, it was a dream at the time, and today we sort of hope to convince you that that's now a viable reality. So the agenda for today, my name is Ben Archard. I will go over sort of an introduction and lay the groundwork for this. Oles, our CTO, will go on a deep technical dive into the implementation and optimizations of ray tracing. Dimitri of NVIDIA will go into a similar deep dive on the implementation of our denoiser. And then Sergey, our artistic director, will take an artist point of view and say what it means to the art teams, and a bit of a walk through our hopes for the future. Okay, so ray tracing, what is it? Well, I'm going to lay down a definition of ray tracing. It's a model for the way that light behaves in reality. Now, every other lighting technique you'll have ever heard of, shadows, ambient occlusion, reflections, caustics, all of these are models in their own right, but their models are a simple aspect of one phenomena that we see of lighting. Whereas ray tracing is an attempt to capture the reality of light, the behavior of lighting as a whole. What that does for us is, one, it could simplify our work greatly. Instead of managing all of these other independent, disparate techniques, we could boil it down into one solid, much easier to maintain technique. But it also offers the possibility that we'll go from a scene filled with faked, unrealistic versions of what light is doing to something much more realistic, something a lot closer to nature, something a lot more believable. And as you can see from the fact that we're using in-game screenshots, we kind of get the feeling that that's what ray tracing is giving us. So ray tracing has been referred to as the quest for the Holy Grail. And I hope that that statement of we believe that this is going to get us much closer to the reality of light in nature should convince you of why we believe that it's the Holy Grail of rendering. And the goal is that it will eventually replace all lighting. It will take the entire lighting scene under the umbrella of ray tracing and get everything done with one simple do-it-all technique. Now, for the Metro Exodus release, we've shipped a single facet, a single part of the lighting model, which is indirect global illumination from sunlight. We don't do it on analytical lights in the scene, and there are still a lot of other actual regular techniques in there. One of the reasons for this is, to keep the optimization reasons behind this, but also because we're about 4 years into a game and it was pretty much on lockdown already. So in order to keep the actual visual feel of the game, we shipped with just the global illumination, but we have done a lot of other work that we're going to demonstrate today, that we've done a lot of groundwork, and there's a lot of other work behind the scenes. So I'm going to explain the changes we've made to our engine. This here is a diagram of a very typical deferred renderer. And the structure of the 4A engine it's typical. It's something you'd be very familiar with. We start with a G buffer where we pre-compute most of the scene's information, normals, depth, material, and information and such. We then have a pass where we build up lighting information for the effects that are going to come later. We then have an accumulation pass where we do sunlight, well, the traditional sunlight calculations under a traditional lighting model. We have a clustered lighting buffer which we paste onto the deferred buffer data, and other screen space effects and whatnot, all in that regular pass. A very familiar deferred renderer, and at the end, obviously, we have a TAA and the various post-process effects. The changes we've made to it, though, immediately after the G-buffer. We still render the G-buffer. We're still rasterizing. That's very important. There's no need to do your first ray probe into the scene because you're only going to end up with exactly the same data. But immediately after the G-buffer, that's when we do our ray tracing. Now, for every pixel, we generate a ray. We use the depth information, the depth buffer, to give us a world position. We use the normal information, the normal buffer, to give us to generate a direction for the ray. So that gives us an origin and a direction, and we use API level calls to cast those rays into the scene. When they return with information, the information that it gives you natively as an intrinsic within the API is the distance to the hit. That's one of the things we store. When a hit is detected, you can also run an independent shader to say, oh, give me some more information about the location. From that, we return a color value, and we store that as well. Now, generally for us, that's the albedo, but it can be any color information. I think that's important to convey, because we're storing a distance value and a color value. So that effectively, for every pixel, gives us some notion of a light source a certain distance away and with a certain color. And we pack those all into our new RT buffer. Now, next stage after that, we have a denoising process. Now, this is a very, very important part of this technique, and we're going to go into it in a lot of detail. But this basically takes that buffer filled with lights dotted around the scene, and it turns it into an actual viable picture of the lighting environment. Later on in the lighting accumulation, we still have a very similar process to where we had it before, where we once upon a time did a regular light for the sun. Well, now we accumulate our ray tracing data along with analytical lights and various effects, and from then on it returns very much to the normal flow of a deferred renderer. So I'd like to take a step away from ray tracing just for a moment to talk about something which is equally important to this process, and that's the stochastic method, stochastic analysis, sometimes referred to as the Monte Carlo method. A simple explanation of this. If you have a very huge data set and you want to analyze that data to get some kind of statistical notion of what's going on, but you have way too many data points to work with, what you can do is you can randomly pick just a few small samples and say, right, I'm going to use those samples as representative. So you end up with a much smaller data set to analyze, and you can do it in a much quicker fashion. Now, of course, that's ideal for a situation where in nature we might have billions or trillions of photons entering our eye every second, and we have a ray budget of maybe hundreds of millions. So it very much lends itself as it's a necessity for this. So what are you going to get out when you apply a stochastic method? Well, first thing you're going to see, you're going to get a buffer of data points generated, which is going to be very noisy and very, very chaotic. You are going to have to apply filtering to that. You are going to have to analyze it. And that's why I would like to emphasize that the denoising process, turning this random just wall of noise coming at you into something that you can actually use and something that gives you a genuine picture of the lighting in the environment, is as important as the ray gathering process itself. There's a few things to look out for. You really need to make sure that you choose your samples well. Like, you're looking for a random distribution of good, solid, representative information. So the key to doing this is making sure you have a good selection of noise. Now, we generate our arrays by, we sample a blue noise map. We use blue noise because it tends towards the higher frequencies. It's a very good random distribution. We sample a noise map, and we use that noise map to produce coordinates on a hemisphere. We align that hemisphere to the normal in the G buffer, and we use that to generate a random direction into the scene. Now, A few other things you want to definitely look out for when you're using your noise. It has to be fully procedural. You need to be able to say, oh, it's this pixel position, it's this frame number, because you will be generating your rays a number of times. We generate the ray at first when we're generating the RT buffer in order to actually do the ray tracing, but because we're only storing the hit location and some color, we're going to need to be able to reproduce that ray later at analysis time. Also, it is vitally important that you have temporally and spatially uniform noise. Look into Halton sequences or things like that if you want to see a good example of uniform noise. If you don't have it spatially uniform, you can end up with aliasing artifacts and moire patterns. And worse, if you don't have it temporally uniform, distributed evenly through time, then you can end up with swimming artifacts, and you might see pulsing of your ambient occlusion and things like that. Okay, so let's take a look at the features we've actually implemented. Now, I said up front that a lot of the techniques like AO and whatnot are supposed to emerge from the ray tracing process. We're supposed to see them, appear natively. So you may ask, well, why should we bother actually still doing something like RTAO, which is a replacement for SSAO? Well, first off, we still have native traditional lights, analytical lights in the scene, which use traditional AO. And also, the actual ray tracing that we use is mainly in the foreground. It's the front 250 meters, after which we transition to a traditional pipeline. So we still need the AO around for that. Now, the purpose of AO, of course, is to say, what's the local environment like? How much general occlusion is there? What other surfaces might be prohibiting light from reaching a pixel? And so how much must we darken it? Well, screen space has a wealth of information of nearby pixels saying, oh, okay, there's a lot of, there may be a lot or there may not be many other pixels around. So we get an estimate of the local geometry, but it has no real ability, like the information falls off as you go to medium or long range. You just don't have the accuracy with a screen space technique. But of course, in the RT buffer, we already have a buffer set up with a wealth of distance information to nearby objects. So we can use that along with screen space information to say, right, this is what the local environment looks like, this is what occlusion at medium and long range looks like, so we end up with a clearer and more accurate occlusion picture. However, we don't actually use this so much in the GI pass. It's used mainly for analytical lights, because they still use AO, and also as a guide for the denoiser. It allows us to confine the parameters and allows us to constrain ourselves somewhat when we're doing the denoising process. So it's used as an optimization for that, but it doesn't have a direct effect, which is why it's not as visible outdoors. It is very visible indoors with regular lights, but the actual outdoor environment does produce the effect of ambient occlusion from the ray tracing model itself. And here we see a replacement for the voxel-based GI. You can see that our original solution was very much just a directional effect. It was a coarse-grained voxel grid, didn't have anywhere near the level of fidelity, wasn't scalable with screen space, so as you zoom in and out, you get an actual scaled representation. And it was so low fidelity that we couldn't get any notion of micro shadows or the close contact interaction of objects. So a few quick pictures. In this, we're showing the initial, the game before RTX, the AO pass, which goes in as fed into the GI pass. The GI pass itself, which is our lighting term now for the actual GI, and then the effect when it's paired with actual ray tracing. Here's an example of a close-up scene. Like, pay close attention to the checker piece next to the pot there. You can see that it's too small to be picked up by a shadow map, but it is, like, clearly, the table is clearly casting rays against it and saying, oh, there's a nearby object. So that's generating nice contact shadows. Here we see an environment that was too open for ambient occlusion, but there is still rays not reaching the outside, they're falling short, and so we're able to say, oh, this is a darker environment. And this one, I mean, this is what GI is sort of all about. You see on the left of the screen a green container, and on the right a white container. Also above the green container there's a red container. So, I mean, obviously this isn't something that could be done with a screen space technique. But the white container is probing the red container with a ray. It's saying, oh, there's some red geometry there, there's some red light falling on me. And so that's how light is propagating around the scene and picking up lighting data from nearby geometry. Okay, so with that, I'd like to sort of pass on to Oles for a deep dive into our technical process.
Hi, my name is Oles Shishkovtsov. I will describe our implementation both from the engine side and the GPU side. Slides will be available online anyway, so I'll try to stay brief. Basically, we remove everything what is related to effects to be replaced with ray-traced version. We have to modify a few stages. Obviously, we had all the bookkeeping necessary for ray tracing to work, and of course, we add ray tracing and the noise in itself. From the C++ engine side, it all looks like completely independent mini engine. It is just 3 source files and less than 3,000 lines total. With the biggest of them being the DXR API management, like shader compilation, pipeline configuration, all that BVH, bounding volume hierarchy stuff. By the way, careful BVH management is extremely important, and for us it is especially important as Matter is instance heavy. We simply have too much of those ray tracing instances. That is why we carefully call them by expanded frustum, in addition to contribution calling. And we always do a full rebuild from scratch of top-level acceleration structure. As for bottom-level acceleration structures, for all the animated stuff like skinny geometry, we only do update operation and never rebuild the BVH. Update itself is fast, but it underutilizes GPU due to multi-pass nature of algorithm. That is why we hide it or pair it with async compute workloads. But here is the problem. If we update everything that was animated in the frame, it would be like thousands of bottom-level structures updates, and then those updates would cost more than the ray tracing itself. Clearly, we should throttle those updates to something manageable, and we do. This slide outlines and describes our way. And there is another optimization in place. The metric content is really highly polygonal. LODs are quite rare. We mostly rely on real-time impostering. It's like cache for G-buffer and shadow maps. But we also have an optimized what we call shadow meshes. With position-only vertex buffer, vertices are merged, indices are simplified. So we use exactly those meshes for building ray tracing bottom-level structures. Sometimes it results in approximately 30% faster ray trace, and always uses about 4 times less memory. Okay, back to the GPU. Basically, we shoot the rays at every pixel in all directions according to diffuse BRDF lobe. In the ray tracing world, it is usually called BRDF, importance sampling, and it is always considered to be too noisy to be useful in real-time context. Actually, no one believed it would be possible in 1 ray per pixel when we started, but we managed to do half ray per pixel in the end. This is the logical structure of pipeline from GPU point of view after all the changes. And that is the real inside GPU trace. Here you can clearly see what is running is async compute, how it all overlaps, and see the relative cost of each stage. By the way, take a look at BVH management cost. It's on the left, and how it is hidden with async compute. I'm going to explain what other ray tracing related stages do next. The first step of ray tracing pipeline is actually screen space remargin. We've used to call it pre-trace. It uses the same rays, and if it can find the intersection in screen space, we use it instead of spawning the real geometric rays. This results in some performance boost for real ray tracing, but more importantly, it fixes a few issues with tolerances and missing alpha-tested geometry. And yes, we try to filter out alpha-tested meshes as much as we can, based on mesh, shader, texture, combinatorics. The next step is ray tracing itself. It runs the same ray generation math as in pre-trace. The first thing what RayGen shader does, it remerges a map of terrain, and if intersection is found, it is used to limit or shorten the ray length. By the way, payload is just single unsigned int. It packs hit distance and albedo at hit point. The next step is slicing and shading of hit points. It is another distinct path, kind of different shading, but for hit positions. Hit positions are constructed by running the same ray generation methods in both pre-trace and ray trace. And we use shadow map cascades from sun directly, but they are constructed to cover the expanded frustum necessary for rays hitting something off screen. For sure, you have a question in mind why we compute contribution only from sky and the sun or moon. Actually, we tried to compute contribution from all analytic lights, but it changed indoors too much away from art direction and interfered with stealth gameplay mechanics. So the short answer would be we were out of time to tweak a lot of content as the technology stabilized it too late in the development cycle. So, we've talked about lighting, but visually important part of GI is color bleeding, and for that we need albedo available everywhere. For pre-trace, which runs in screen space, it is simple. When it finds a hit, we just sample the albedo from G buffer. But for real rays, which of course can go off screen, we use different technique. We store average albedo per ray tracing instance and sample it in a closest hit shader. That is essentially a pre-filtering of signal. So this way we get less noise in the GI itself. But in addition to that, it is extremely fast. Isn't it too coarse a presentation? Yes and no. The color bleeding is mostly visible on the close-to-contact surfaces, and those are usually found in G-buffer. And for everything else, because matter has a lot of instances, pre-filtered albedo works great. We hit a few troubles along the road with that approximation. Initially, for instance, albedo was calculated from average texture color, but sometimes the color seems to be slightly off or completely incorrect. Usually that's because of texture atlases or complex shader, which modifies albedo in an unpredictable way. What we did later, we pre-render all meshes used in game from different viewpoints and average that exact albedo. That solved almost all the issues, but we still allow artists to override that with custom albedo. This is how it looks in game. You can clearly see the bluish and reddish accent of reflected light. But what is also quite visible here, that is the sharp normal map details from indirect lighting. Usually any denoiser will blur such teeny details away, so how it works here. Let's discuss very important topic, irradiance storage and encoding. What we do at the very end of the light and shading path, we convert HDR signal into YCOCG color space and store Y as the first order spherical harmonics. So we use 4 coefficient for Y and 2 for COCG. So it's 96 bits total. And all the accumulation and denoising works in this space. 96 bits to store and especially sample multiple times during denoising sounds really scary. Maybe we could get away with just color. Tried that. That was the first implementation. Non-directional color space just doesn't work visually. It looks like a blurry mess. We've tried to reduce bits here and there, but failed. Not enough precision for us. So 96 bits is what we shipped Metro Exodus with. But the really nice property of such encoding, it is actually a low-order approximation of cube map and at each individual pixel. So we can compute indirect specular, and specular is really important component for any PBR pipeline and materials, especially for metals where albedo is 0. So for diffuse component, we simply resolve SH against pixels BRDF, but for specular, slightly more complex processes involved. We extract dominant direction out of SH and then compute degradation factor, which basically says how directional the SH is, or is it degenerated to ambient after all the accumulation and denoising going on. And if it's mostly ambient, it basically means that light is arriving at this pixel uniformly over the hemisphere. That's visually the same scene as if material is rough. So we recompute new roughness and then run regular GJX with extracted direction and new roughness. This is how it looks in game with indirect specular turned off. So that's diffuse only GI. And this is with it enabled. Also, it is mostly visible on the metals. I'll flip a bit. It is in fact affecting every surface. For example, rough floor to the left or wood to the right. Okay. Now some interesting side effects of our implementation. BRDF importance sampling doesn't care what to integrate at all, and what if it puts something emissive into the scene. I'll show you a small demo.
Would it be possible to hit the lights off for 2 minutes? Maybe?
Оно будет показывать?
Давай пробуем.
Дисклопа сейчас не видно.
Hey, we fucked up.
We can turn the monitor.
Yeah, we have a video here that we cannot really show. Drag it somewhere, maybe.
Подожди. No? No?
That's something we didn't test. Can you drag this? Yeah.
Yeah, great.
Power user.
Just a second. Got it. Okay. The thing you see, actually there is no lies here at all. It's just a few emissive surfaces put into. The pipeline is not modified at all. It is still running in a Metro Exodus engine. But what is really interesting here, so yes, that's usually called an area lighting, but it's arbitrary shaped polygonal area lights. And what is especially interesting, that's the soft shadow you can see from the arbitrarily shaped polygonal lights. So again, there is no license here at all, just a few emissive things. I'll try to continue. Okay. So that's already what I talked about. Just a second. That's not it. I messed it up again. Yeah. Here. Okay.
Drag it onto the other screen.
It's already okay. So I'll summarize a bit what I talked about and what Metro achieved. That's a real-time global illumination pipeline, also capable of direct lighting and shadowing from arbitrary shaped polygonal area lights. And when I say real-time, I mean the new definition of real-time. So it's 60 frames per second or more, and at high resolutions. Everything is fully dynamic: the camera, the geometry, the lighting. So absolutely zero precomputation, and all of that is running in a massive world of Metro Exodus. What we will continue to talk about, it's how intrinsically noisy BRDF sampling is, and how it could even work at all with half array per pixel. I'm done. Thanks.
Thank you. So first of all, in addition to Alex's words, so if it wasn't clear, this demo was completely ray traced. So without ray tracing, it looks completely black and dark, and this upgrade will be used in the upcoming Metro updates and upgrades. So now with my part. So hi, my name is Dmitry. I'm an NVIDIA DevTech engineer, and I have been working on denoising in Metro. First of all, I'm just another guy with strong Russian accent, so just relax, don't think about it. You can think about it like about a voice from a Red Alert game, so no worries. Denoising, what is it? Denoising is a process of removing noise from a signal, or at least we want to lower it, and it can be convolution or deep learning based. Our approach is convolution based and has spatial and temporal components, and it's worth noting that a deep learning based solution sounds very interesting, but it's barely explored in real-time graphics, so we decided to dedicate Turing Tensor course to DLSS. Just for better understanding which beast we are facing at, denoised image is on the left, noise input is on the right, and I want to say that the image on the right doesn't use any kind of accumulation or denoising applied, so it's just pure GI computed using only half ray per pixel. The same image, just noise input on the left and denoised image is on the right. I can switch a few more times so you can compare. Just for emphasizing the complexity of the problem, casting rays is fun, but denoising is not. So image quality is always bad and sad, and tiny change can break everything. Even if image quality is good, then performance is bad, and vice versa. And theoretically, you can spend a lot of time investing into a single pass denoiser, but it won't work well. So how many passes are needed? Actually, denoising can be decomposed into two components, spatial and temporal. So speaking about spatial component, we need to cover the following topics like sampling space, distribution and radius, how many samples are needed, how to compute sample weight. And for temporal components, the most interesting thing is temporal feedback, its direction and strength. The first component is spatial, so what is it? Actually, you can think about it like about a single pass blur. Just take a lot of samples around the current pixel, which is our point of interest, and accumulate a weighted sum. The weight can depend on the signal type, and actually by the definition, it's Monte Carlo integration, so some kind of. When we have a deal with a blur-like filter, we need to choose sampling space. So screen space or world space. Probably the most obvious way is to use screen space and just work explicitly on pixels. But it's a bad idea. In practice, it doesn't work well on surfaces at glancing angles due to anisotropy naturally caused by perspective. And in this case, a lot of samples will be taken from places which are too far from the point of interest, and as a result, we will be accumulating a sum with almost zero weights. It's not what we want. So how to solve this problem without inventing some kind of anisotropy sampling? We can just switch to world space. We have a normal, we can construct a tangent basis, just construct a new sample on this basis, project it back to the screen, and the problem will be automatically and naturally solved. Again, by perspective. Some words about importance sampling. Strict definition of Monte Carlo definition introduces probability distribution function. It's a bit complicated, but we definitely want to take more samples at locations where sample weight is larger. So what do we need to do to achieve that? Probably a common approach is to use a uniform distribution, probably like a Poisson disk, with some nonlinear mass applied for distance weight calculation. It works badly in the reality because our space is discrete. So what we can do, actually Monte Carlo integration allows us to migrate or to embed our nonlinear mass into the distribution and just replace it with linear mass or even a step function. Intuitively, we definitely want to take more samples around the point of interest. So in Metra, we use quadratic distribution for denoising, and sampling is done at world space. Okay, so we have greatly simplified distance weight calculation, but which samples are important inside the disk? Mostly we're interested in samples located on a tangent plane, computed around the normal of our point of interest. Plain distance can be used to calculate smooth fall-off, but it's worth noting that we are also interested in samples with negative distances, because otherwise denoising just will skip all rounded objects, and it's not what we want again. Additionally to distance weight, normal weight can be used, and I have seen some solutions which apply power function to n.n factor to fight with blurriness problem. Actually, it just don't use this. It's a mistake, and because it's physically incorrect and makes your GI or ambient occlusion very oriented. But using just a pure n.n factor is a good idea. And of course, we use that. We will cover that a bit later. There is another obvious idea floating in the air. So let's use random per pixel rotations. Just don't. It's a very bad thing. It leads to significant slowdown due to serious cache trashing. And actually, so why? Because you can think about it like applying noise on top of noise. Our signal is already very noisy, so it's not worth it. But using per frame random rotations, which are constant fall pixels in the frame, is a good idea because it can help to improve temporal accumulation at no additional cost. So radius of denoising, or how wide should be our blur. Skipping unnecessary details, it needs to be large, but can be scaled with distance. Variance is our friend. By the way, variance is the deviation from the average of some samples. The idea is to blur less if variance is small. Else, it's a cheat, but we can use ambient occlusion to blur less in dark corners. At least it works in most cases. And another good idea is always to use signal-to-noise ratio and blur less where the noise signal contribution to the final image is small. How many samples are needed? 32, 64, or even more. The idea is to compute variance of the input signal and adaptively adjust number of samples. And of course, it sounds good, but we have a problem because the variance computed for the input signal only is always a big value, so it just won't work. So it's time to introduce a new component, which is temporal component. Temporal component, it's something which reproduces the accumulated history from many, many previous frames. And there are two common ideas. We can use temporal accumulation, do temporal accumulation before denoising or after denoising. If it's done after, it leads to more stable low frequencies. If it's done before, it leads to better high frequencies because variance will be greatly reduced. But we don't use that. Our idea is to mix up high frequencies coming from the current frame with low frequencies coming from the history buffer. And actually, you can think about it like about a recurrent blur. The benefits are more various frequencies over time. It requires less sampling per frame, less samples per frame, and it leads to less hosting. I will explain a bit later why. Image on the right is actually our ambient occlusion denoiser. It uses up to 64 samples with adaptive sampling, and it tries to share a single ambient occlusion value between 2 pixels if there are no edges. There is no edge. The most interesting thing, so it's time for the most interesting thing now, it's our little monster. It's the GI denoiser. It consists of 2 passes. Actually, it's a chain of 2 blocks from the previous slide. Dashed lines show borders between passes. So let's deep into the details. A single denoiser block. It computes variance of the input signal. It computes radial scale in 0-1 range. Then it computes adaptive step as a function of radial scale. And in the loop, processes each nth sample taking up to 32 samples, but not less than 4. And at the very end, the combiner just mixes up the input noisy signal with the denoised signal. Usually the ratio is 50-50%, but it can be shifted towards denoised signal if something bad with history buffer is detected, like sampling out of screen, or the occlusion is detected, or just pixel velocity is high. Temporal accumulation always happens before denoising to eliminate coasting and reprojection artifacts. Why? Because denoiser just blurs out all problems. Else accumulation greatly reduces variance, what leads to reduced radius of denoising, of course, and improves performance. Probably good advice, at least based on my experience, that don't cheat with history. If the occlusion is detected or sampling out of screen, then just reject it. It's a bad idea to use it in this case. A combiner just uses lerp function to mix denoised and noisy signals. It helps to preserve tiny details here and there. And don't forget that the output of each pass goes to a temporal feedback, because our idea is to accumulate various frequencies and avoid accumulating long, low frequencies only. Because even spherical harmonics resolve won't be able to hide all artifacts if low frequencies only get accumulated. First pass of denoising doesn't take normals into account, mostly for performance reason. It's wider than the second pass, so normals probably are not needed. This pass is done at half resolution for RT high preset, and it's always done at full resolution for RT ultra. The second pass of denoising has smaller base radius, so it's up to 3 meters, and I need to say that 3 meters is the base. This value is almost unreachable. And it takes normals into account. And it's always computed at full resolution to preserve details. And no magic, so it's the same denoiser which applies normal weight on top of the geometry weight. So very short list of denoising tips and tricks. It's funny, but on Turing GPUs, blur-like filters can be easily shader-bound, ALU-bound, or mass-bound, and not texture-bound or memory-bound, as you expect. So don't forget to optimize your mass, and please use on-site graphics to understand your limiters. It works perfectly in our case, so our data is very heavy, so we don't fetch data if the weight, the sample weight, is almost 0. Temporal accumulation is your friend, so you can just think about it like about free pass of denoising. Of course, spherical harmonics, irradiance is your friend too, so it's a bad idea just to denoise color information. Don't do that. Convert to SH and use SH instead. And as always, know your noise. So there is no need to reach the perfection in image cleanness, because applying albedos, various post effects, TA, and even camera exposure just hides many problems. Some words about the performance. So for RTX 2080 at 25 by 14 resolution, the most interesting thing is that BVH updates are completely hidden by async compute work. Ray tracing performance, of course, greatly depends on the resolution, so we use 1 ray per pixel for RT Ultra and half ray per pixel for RT High Preset. Denoising performance barely depends on the content, so it's somewhere around 0.6 milliseconds for ambient occlusion denoising, for example, on this particular GPU, and resolution for RT High. And as a result, RT High overhead is only 22%, and what makes us best in class. So that's it from my side, and probably the most interesting side, the most interesting thing. Sergey, please.
Hi everyone. So my name is Sergey Karmalsky. I work at 4A Games, and I'm doing the art direction thing there. And we have released Metro Exodus with RTX like a month ago, but we've been working with the tech for more than a year now, and we as you can see, but we have something to share. And the reason basically I'm here, it's a programmer dev tech talk, right? And I'm an artist, and I'm just showing how it's gonna work from the production side, from the content production side. I will tell you our team's experience. Also, I will be showing you pictures, and hopefully that will be slightly entertaining. So, a little bit of history. So we've released a demo about a year ago, and we've been really happy with the technology. We've been really happy with our achievement at that time. But unexpectedly, there has been some concerns from the world. We started seeing those reactions. Is it really that technology is worthy? And weirdly, those concerns were also inside the company as well. We already had quite a lot of working solutions, proven solutions for ambient occlusion and for GI. Like, for example, the SSAO does AO, obviously, and we had the voxel GI working, doing the reflexes from the sun. And so why bother? We also know, and basically all developers know, how limited those options are. And we even got used to them somehow, I don't know. We cannot really do proper GI. We only can bake it, so it's not a real-time solution. And the SSAO itself, it just suffers from its screen space nature. So you will always see that problem with edge fading, and you will have no data behind objects, and that's really a problem. Another problem with the SSAO is it's mostly limited to a short ray distance, and weirdly we got used to that. But really, 1 meter is the best we can do. It even gets expensive at that. And effectively, in large scenes, in canyons, in cities, that's like an edge trace effect. And I'm really not really happy. So I know that that's not the proper way, basically, to do occlusion. And then we met those insane possibilities with crazy numbers. So we are right now playing with ray lengths which are 50 times longer, and we are getting unbelievable amount of those rays per second. And also, what is also really important, that we are getting the pixel perfect details. So we are not limited by the scales of the scenes. And this is an example of the same street scene, and you now understand what I'm talking about. So I'm talking about large-scale occlusion and large scenes, and that's really important for me, obviously. So no more edge trace effect. You are getting the proper large-scale occlusion. And another example is this natural scene. You can really feel you're located deep in the canyon, and that's thanks to proper skylight occlusion. And this one example is a small-scale scene. And with fixed ray lengths, we are not really getting all those details when we zoom in into something. So any super close interactions, they will be lacking that proper AO. And this is an example that the ray traced GI now, what allows us to have. So you can see how objects are grounded, and you can see how objects pop up from the background. So everything is much more readable now. A revelation I had is that the SSAO and the ambient occlusion pass is no longer actually needed. So we've been doing that, we've been multiplying that on shadows for so long that I got used to that so much that I thought that it's happening in real life. But no, 20 years ago we've been playing with the first implementations of radio OCT rendering and stuff, and that's the proper way to basically calculate occlusion. So right now that all is happening in real time, and no more multiplication of that buffer, AO buffer, is needed anymore. So this happens properly by GI occlusion, right? And you can see in this, and this working, luckily works. This animation, there are no direct lights here. You can only see light coming from the sky. And the sky is basically HDR picture with some areas that are brighter. And effectively, that type of solution produces shadows. So the ambient occlusion itself is no more. These are real shadows. That was crazy for me. The next step, obviously, we had to go on and do the GI from light sources. And this is an example of how light sources, the sun specifically, been illuminating interiors, and we've been getting GI only from the light probe. So the room here was capturing some proper amount of light that entered and illuminating that room naturally. So it looks just natural. It was filled with natural amount of light. But the ray trace solution is giving an absolutely different result. So in terms of overall brightness, the pictures may be the same, but in terms of detail, you can see the difference. You can see the small scale. On the very right, there is a box on the top, and you can see how light is reflected from the bottom of the window. And all objects, really, they pop up. And it also feels like the objects are related to each other, because you are getting that existence of a neighboring object visualized by light reflected. We went on, and as always mentioned, we had to go for the specular GI as well, because obviously the PBR techniques are requiring the specular pass, requiring the light from the specular, and sometimes it gets up to 50% of light through specular, and not mentioning even metals. And the color bleeding itself is a great way to basically demonstrate GI itself. So without color bleeding, at some point we didn't feel that the reflexes were there. So basically, when materials, they share their color property, that's clearly visible. And an example, so color bleeding off, that's actually no ray trace happening is here. But the image was quite okay for people. So when the first time they saw this image, they was thinking, is this RTX on? Nope. This now is RTX on, and you can see all the small occlusions, all the light bleeding effect, all the color bleeding effect. So you can see the blue and the red, and everything looks fine. So when you go back to that image, you understand that you will not want to go back from RTX anymore. And besides the implementation of the technology itself, we had to do quite a lot with the content itself. And we, obviously, the RTX solution was slightly different. At some point, not slightly, but really radically different. We even got some feedback on that, negative feedback. And we had to fix the scenes to make sure that they will be properly working under the ray trace solution. And we had to remove all the fake lights. So they were not working properly anymore. So all the artsy stuff, all the gameplay comfort lights, they had to be removed. And because the RTGI been bringing in its own light over there. And we also had to adjust the standard version itself in cases when the RTGI been given the radically different result. So we had to bring those two versions together. And what's also pretty important, even though we were quite excited with the tech, we couldn't allow ourselves to overplay with that, just because in further comparisons, we didn't want any version to be a loser. So both needed to look really good. It's basically Metro versus Metro. And then this happened. It's a deadline that always happens, so we just had to get drunk. So basically, all the work stopped, even though we did work on some patches, but we have successfully released the thing, and I'm pretty happy with that. And about those concerns, and we are pretty fed up with those, frankly, and it continues to happen even after the game is released. So we see that people are trying to judge if the technology itself is doing any better for the picture. And we've been doing the same initially, but we understood clearly that that's not just the right way to do. So we are getting a different result, and that result is realistic, more believable, more natural. So I suggest the word convincing. So which result is more convincing? And an example. So many people thought that this is an image with RTX on, but no, until they saw the more convincing result. So how do we use this? So basically, we're happy with an achievement, and that happiness this didn't fade off yet. We also are happy with the fact that RTX does everything dynamic and doesn't require any pre-stored stuff, because doing dynamics is just one of the pillars in 4A games. We don't like pre-bakes. We just hate those cuffs of static stuff, static data. We are also using this tech in development, and we're using this as a lighting reference tool. And specifically, we check first what RTX gives us, and then we continue with developing the final lighting in scenes. That's a pretty useful thing to do. Sometimes it even brings us random ideas that we didn't expect. Like, for example, this here, I've been making a screenshot of our Anna character, and I've been playing with an idea of doing a dark silhouette with contrast light and a rim lighting behind, until RTX showed that the result the feature may be absolutely different. You can see here that the character lights herself up from her own reflexes and from the reflexes from the weapon. And that's something you don't really think of first when you're creating some imagery. And what's next? These are basically, half of this is not dreams, so half of that is something that will be available quite soon. Oles has already been showing you the working demo of polygonal lights, which are actually casting those soft shadows. That's really amazing. We're really playing with that right now. And I really hope that at some point, the ray tracing thing will solve a lot of our problems. We have a lot of ad hocs. All developers, basically, they have a lot of rendering ad hocs, and all those are causing some conflicts maybe, or that you have to solve. And I hope that the ray tracing itself will fix that, will help us with that over time. And finally, I hope that at some point, the RT thing will get on consoles. You all know that PC is a trendsetter, but consoles are standard keepers. So we need that on consoles. Please, if developers are here that are working on that, please bring it. And we'll have yeah. So I'm done. Basically, I'm close to the final slide. And thanks to that person and to that person and to that person, and all the developers and everyone around. And take a look at the link over there. We've been delivering quite a lot of useful information, but maybe too quick. And all this will be available by the links. You will be able to get that now even.
And just a few more seconds. We also have nice bonus slides. So for programmers, you can steal some useful code, how to convert color to GI, back and forth, so how to play with it. Don't forget it. Thank you. And it looks like we are running out of time, so for Q&A section, just catch up in the hall, and we will know absolutely everything. Thank you again. And just a second, Alexei. Raffle. Something is going.
Спасибо.
Yes, I think everybody should get a ticket, and we're still going to raffle Ray Tracing Gems book. And let me try to be quick. So winner, oh sorry, winner is 603327. Can. Okay, cool. Thank you.
Thank you very much.